Hello and welcome again. So today we'll be looking at the control of the half bridge converter. So let's recap what we did in the previous session in my previous video. So what we did was that uh, we modeled the half bridge converter as suggested in the book that we are following, um, and we saw how that system behaves, how the whole network behaves when we change certain parameters. For example, you can see that on the screen. So we changed the m, which is the modulation signal, at 1 seconds, and we saw that when we change it to a higher value, we get a higher current. And similarly, we saw what happens if we change the source voltage, or when we change the DC voltage, right? So let's see once. So at 1 seconds, we change the modulation signal to 0.685. So when it is increased to a higher value, we get a higher value of current. And similarly, we get a negative current when the drop across the RL branch was negative, because the source voltage basically was increased to a higher value than the terminal voltage, right? So from here, what we can conclude is that um, if we are supplying power to the grid, let's say the source side is grid, and this is our, let's say, system impedance or grid impedance, and we are controlling our converter. We are getting some power from let's say these DC voltage sources, and we want to control the power that is being delivered to the source side, to the grid side. So how can we control that power effectively, efficiently? And one of the things that we saw is that we can change the modulation signal to change that power. Basically, we were changing the current, we were basically changing the power, the amount of power that was being delivered to the source side, right? And there are other methods which we can do it. Like, for example, let's say if the source voltage drops to a lower value than 400 volts, then also we would see there is a higher power getting delivered towards the source, right? Because there would be a huge a higher voltage drop across the system impedance, right? But that isn't recommended, or that isn't very usual, because our grid is mostly stable, and we don't really we want to control our output. We want to control the output of our converter, right? So we don't really change the source voltage or the DC voltage. We set it to a fixed value. We try to set it to a fixed value, but what we can do is try to control these IGBTs, these power electronic devices. We try to change in a way that we get our reference or whatever power or current you want in the output, right? So one of the effective ways to change M. Now today what we'll see is that, what if I have a reference value. I have a reference value, let's say it's 1000 amps. I want 1000 amps to be delivered towards the source side from terminal, right? So I would think about a control functionality where I, as an input, as a user, as a user, I'll just give an input I reference, which would be, let's say, 1000 amps, and that control would change the value of m, the modulation signal, in a way that we get that output, we get that v reference values in the actual circuit, right? And how we can do this is basically a closed loop control. So we'll be having some a reference value, which will be a constant value, which is the user driven value, which as a user I will give that I want 1000 amps. And there would be at the same time, that control functionality would have the feedback from the plant or from the system. So basically, this current that we are measuring here, we can take that as the measured value, and we take the reference value and try to get that error between this reference and I to zero. And how we usually do that is through PID control or PI control. So today that we would be focusing on the control through the PI. So let's see. So yeah, so that's the third chapter of the book, that is control of half bridge converter. We were controlling it before. In the previous video you saw that we were actually controlling the current, but we were manually changing things. We were manually just changing M. maybe I will have a particular set of values of m, where I will have a particular set of currents in the output. Let's say for let's say for m equals to 0.68, I was getting 1000 amps, and for 0.685 I was getting 1500 amps. For m equals to 0.70, I will get, let's say, 2000 amps. But I don't want that kind of manual control, or what we say, a fixed value. What I want is that I just want to give a I reference, that this is the amount of current I want to be delivered, and you do it. The controller would do it for you. How it would do it? It would change the m value somehow, and that would be changing basically how our IGBTs turn on and off, and then we'll get that particular functionality, that particular output at the terminal. So let's see, the first equation we see is defining the dynamics of our system. So if we just write the voltage drop at this point, so Vt minus Vs is LdI by dt and R plus R1 into I. So that's the normal dynamic equation of the circuit. And what they've done is they put it into a uncontrolled model. So basically, if you are changing m from here, you'll get a particular I in the output, and these Vs and Vdc by 2 are constant, right? So, and yeah, from the previous chapter, we derived that Vt is Vdc by 2 into m. So if we go back to um, our results, what we see is that the that the terminal voltage, if you calculate it, then it would be, so let's say it is what, 411. Let's say it was 411. How it came out to be is, yeah, so what we saw is that the voltage at for 0.685 m, we were getting the terminal voltage as 411, which we can also see from here. Let's say the VDC by 2 was 600, right? And we multiply it with 0.685. That's it. So that's the formula that they have derived from the various graphs. If you want to look into that equation, how VDC by 2 into m came out as the terminal voltage came out as VDC by 2 into m, then you can just revisit chapter 2 and see the graphs and how they have derived it. So if you see it here, we have the VDC by 2 is at 600 volts, and 0.685 is our m. So we are getting 411 at the terminal, right? So what they've done is that they have defined our system. This is the dynamics of the system. So whenever we have to, or we want to design or define or model the control of a particular system, first we need the system equations. We need the system equations to have the relationships between a particular set of inputs that go into that system and the outputs that the system um, gives, right? For example, let's say it's your car. You want a particular speed. Let's say speed is your output. You want a particular speed, so your input would be the amount, or the angle by which you move the accelerator, right? So that's how, and for defining a relationship between the output, which is your speed, the speed of your car, and your angle theta of your accelerator, you need a relationship between them basically, and we need to have some equation about it, so that we can define the system and work upon it, right? So that's what they have done. So this is the dynamic equation of the what's happening here. And when you replace Vt by Vdc by 2 into m, so m would be our input and I would be our output. So that's what is given here. So it's in a control. It shows the control model of the converter. This is basically the dynamics of the converter shown in a controlled form, right? So m is our input and I is our output. Apart from that, whatever you see is fixed values, R on, or your L, Vs, or VDC by 2. Okay. Now what they've done is that for designing the control of the half bridge converter, what we want to do is that at this side, on the right hand side, this is our half bridge converter that we saw just now, this one, right? So what we were doing is, in the previous video, that we were changing m manually and we were getting some I, right? This is just a form of let's say if I don't really model this, I don't need to model this at all. I just model like this. I just put some values. I put a transfer function, and it would give me the same results as we were getting here, as we were getting with the system defined or system modeled here, the whole system modeled. Yeah. Now what it says is that to change our I, we want to change the M, which is our modulation signal. And as a user, as a input, I just want to give an I reference. I just want to give that. I just want, let's say, 1,000 amps or X amperes, and you give me that current only. I don't care about the M. I don't care about the modulation signal. You design a controller in that way that I just need to give a I ref. So what they have suggested is we put a PI compensator, or what we call it as a PID controller. So that a closed loop PID control, what it would do is it will take the reference, it will take the actual current, get their error to zero eventually, and form the M. It will keep forming the M until the current, the reference current reaches, the measured current reaches I ref, or the difference of these two currents, I ref and I, goes zero. So that's how it is defined here. Now what we'll see is we've been given this example, and let's try. We'll try to model this. We'll take the model that we saw last time. We'll take that only, and we'll work upon that. So let's see our model. Yeah. So just to clarify about the half bridge converter in a control format, we can do that here. So let's see. Okay. So when we see the control, yeah. So we have a constant M. Let's say this is our M, right? And we multiply it. So product multiply M by VDC by 2, which was 600, right? 600 volts. VDC by 2. Okay, and this goes into a multiplier, and then we subtract it, right? So we'll put it here, and we'll put VS. VS was 400 volts, if you remember. So it is 400 volts VS, right? Okay, this number VS. Okay, and then we need this transfer function. So I'll put transfer function. Okay, let's see. So this one corresponds to the numerator one. Okay, and we need L and R values. We didn't see any R on right the last time, so let's use the values of L and R. So I think L was 690 microhenry, yes, and 5 millihenry was our resistance, right? So with S we will have the 690 minus 6, right? And R was 5e minus 3, or 5 millihenry. Okay, you can see it here. So 690, that is L, S plus R. Okay, and this is our output. So we'll see the scope. So this should give my current, right? So at M equals to 0.68, which was our initial value, 0.68, right? So what was the current? We'll see. So it was around 1615, right? 16116, or let's say 1600 amps. It was 1600 amps. So this should also give me 1600 amps at the output, right? Because this is basically the mirror of power. See, so this is giving us 1600 amps. And similarly, if I put it, let's say 0.685, what it should give me is, so what it should give me is around 22, yeah, 2.2 kiloamps or 2200 amps. Yeah, so let's see. Yes, so yeah, that's the value of current we were expecting at the output, right? So yeah, this works. So they just defined it, right? Now I would just let it be here. We don't have to do anything about that. We'll just put it here. Okay, yeah, now I want my compensator. I have my PID controller here, and let's see. So what I'll take first is we'll see the example first, sorry. So yeah, this is my example. So everything is the same value, we just have a new value of R on. So R on would be in the IGBT, right? So if we see again, the R on is the IGBT R on. So we will put 0.88 milliohms. Okay, so R on is 0.88. Yes, 0.88 milliohms, 0.88 milliohms. Okay, and everything is the same. Now we just want to build that PID controller. Okay, so this is not required because our PID controller would give our RAM as the output, so we just remove that. Now what we need is I reference. So as a user, I'll put a constant in the I reference, right? So as an I reference, I'll give, let's say initially I'll just put 1000 amps. Okay, or let's just delete, I'll put a step. We'll put a step change to see the change, and I think the book also does the same. It changes it from 0 to 1000 amps, and then thousands to 1000 to minus 1000 amps. So let's see, step time, let's say at 3 sec or at 5 seconds, we want the current reference changing from 0 to 1000 amps. Okay, and this should go let's see, yeah, this should go into the PID controller, right? PID controller. Yeah, so we just need a PI control. So this is how our PI control PI compensator looks like, right? So we will put KP, it's basically KP plus KI by I, as if you remove the brackets, right? So in this one we'll see PI controller continuous time, right? And ideal is like this, parallel like so, P plus I by S, and P and I are KP and KI basically. So yeah, this is the format we would be using. So the KP value is 0.138. Okay, and KI is 1.176. all right, okay, we have put the PI controller. Okay, and then this has to be divided by VDC by 2. So we'll take constant, which is VDC by 2, which is 600 volts. VDC by 2. Okay, oh, this shouldn't go here because we'll have a subtract, right? Subtract from the actual value that is flowing through the actual system, right? So we'll put it here. Okay, divided by this. So we'll take divide, and yeah, if you see this, the equations in the previous chapter, it says that m has to be the mode of m has to be less than equal to m1. So its span is from -1 to 1 basically. So we'll just put a saturation block. So saturation, so this is what I was talking about in the last video. So each and every output of this controller, or each and every set points or parameter has to be limited, has to have a upper and a lower limit. So just for the protection of the whole scheme of the whole system, right? So I'll just put 1 and -1. You can use some lower values than 1, because I think at 1, if you check the system for m equals to 1, the current would go around thousands of, like 34,000 or 35, 36,000 of amps. So I think that's it. We'll get our m here, and this is the same m would be compared with our carrier signal, and then we'll have our Q1 and Q4 switched. So this is the I reference that we give from 0 to 1000 amps at 5, and this is the actual current. This is the actual current, right? So we'll take this. Yes. So it will keep seeing, the controller will keep seeing the current and try that this measured current should follow our reference. So at 5 seconds, it will try to get the current to 5,000 amps by changing the amp. That's it. So as a user, I just have to define the amount of current I want. Okay. So this should work fine now. Let's see how it is. Let's see the current. Okay. Yeah. So you can see that it takes some time for it to stabilize, and we'll be looking into that in maybe the next video. But as of now, what we see is that until 5 seconds, its reference was 0, and after 5 seconds, I changed the current reference to 1000 amps, and it goes to the 1000 amps eventually, right? And this is the normal the response of the PI. So what we observe here is with the KP and KI values that are already defined, right? But what if I don't have the KP and KI values? So for that, they already mentioned it in the example that for a closed loop time constant of 5 millisecond, they decided on the value of KP and KI, and how these KP and KI could be driven is from this equation. So what it says is, when you see the closed loop gain of the whole system, then you'll find this equation, right? This is the gain of the whole control system. Now, when you elaborate, or when you calculate this R plus R1 by L, it is quite close to the origin, right? And that makes our the response of the system quite slow, because if you go to the basics of the control theory, then uh, uh, as far as you go from the origin to the left, then your system acts faster. You'll get a faster response of the system, right? So just to cancel it out, what they choose is that they'll choose the Ki by Kp value such that they equals to R, your pole value. So that's what they have written here. So they will choose Ki by Kp as R plus R1 by L, so that the poles and zeros get cancelled. And what you'll have now is the desired time constant, which will depend on the Kp by L. And that's how you can get your Ki and Kp values. You just need to choose a desired time constant of your closed loop system. What they say is that when you are choosing the time constant of the closed loop system, that you should keep it smaller, obviously, because with that, if you keep it small, the time constant, if you keep it small, then your pole would be very far away from the origin, and that would mean that your current control response would be faster, but it should be large enough such that your bandwidth is small. The bandwidth of your control system, closed loop control system, is smaller. So that's what we see here, right? And further, what you can do is you can change the current from 1000 to minus 1000 amperes and see this how the system responds. So it will go, it goes to 1000 amps, and then it will go to minus 1000 according to whatever reference you give as a user. And they also provide us with m values, how it changes. You can just monitor it together within your simulation. And for power, what you can do is just take the current here, right? The current, average current, and the average voltage, you multiply them, product them, and see it in a scope. So you'll get similar kind of results, right? And that's it for this video. I hope you learned something from it. And the major part would be how we represented the system, the actual system, with the IGBTs and all, everything with a dynamic equation. And we even verified it that it works very similar. It gives the same results. And we saw how to design or model this controller where as a user I just want to give the reference current as an input, and the desired current, and the controller will do all its manipulation, all its calculation to get that M, and then it will give our desired current value in the system, right?